Okay, so then let's go over F9 as planned. This is another type of Atwood. We have a horizontal table. We have block B, on top of which another block is attached, and both are connected to a pulley. And the table is horizontal. Let's imagine that F is subjected to an horizontal force F towards the left. This time they don't give us the mass, they give us the weight. So we know the weight of A, we know the weight of B, and we know, and we're given all the coefficient of friction, μs and μk. Therefore, we know that there is friction between B and the floor or the table, as well as between A and B. Find the magnitude of the horizontal force F to drag the block B to the left at a constant speed. What is the keyword here that would allow us to identify which law we're going to use? Excellent. Constant velocity tells us that we have a constant velocity, therefore Newton's first law is going to be used. And, wait, how come my pen got thicker? There we go. And we know that we have two subsystems A and B, therefore we're going to use the third law. B on A is equal to F A on B. So both laws will have to be used. Okay. If F is horizontal and is pulling object B towards the left, obviously B is going to move horizontally towards the left, and A is going to move on top of object B horizontally towards the right. Okay, perfect. So let's apply Newton's law. We're looking for force F. F is applied to B. So, well, let's start with object B. First force that comes to mind is the weight. We are doing object B, therefore this is the weight of B. Since they're giving us the weight and not the mass, we can write this as WB instead of MBG. So we don't have to multiply the weight by 9.8 anymore. What is the second one that comes to mind is the normal force. The normal force shows up every time our system is in contact with other systems. How many contact does object B has, or how many normal forces do we have to consider for object B? Excellent. Thank you, Dyson. One is going to be from the floor, parallel to the floor surface, acting on object B. Therefore, this one is up. Let's call it an F. And then there's a surface between, or contact between B and A, which is on top. Therefore, there must be a normal force coming from A, acting on B, parallel to the surface or the contact between A and B, acting on B. Therefore, this one must be down. I'm going to call it NAB because it's between A and B. You will notice that I haven't used the weight of A. The weight of A has no place in the free body diagram of B. Even though, as you've done this problem before, for today, you have realized as you solve for the equation that NAB will end up being the weight, but that's a very specific case. So in general, we want to do this because if there is an incline, then if we take that assumption, we're always going to have problems. Perfect. Then we have any pulling, pushing. Yeah, well, we have F that is pulling towards the left, and we have the tension that is pulling towards the right. All right. All the forces are vertical, horizontal, up and down, left and right, so easy. Before we complete our free body diagram and write the equation, since we have more than one system, let's write a free body diagram for object A as well, because then we're going to be able to use Newton's third law. So object A, first is the weight, WA. Then the normal force, obviously A is in contact with object B, B is below object A, therefore there must be a force coming from object A acting on object B. From object B acting on our system A. Therefore, this normal force is up. Oh, yeah, thank you, Ray. Friction. That was the last one. Thank you. We're given US and UK, so we need to have friction. Where is the direction of friction? And what kind of friction are we dealing with? Since we're moving at constant speed, are we dealing with kinetic friction or static friction? Kinetic. Excellent. Be careful. Mu-K is not a friction. Mu-K is a coefficient. We're dealing with Fk. Keep that in mind. There is a difference between the two. Let's not mix up the two. So excellent. We're going to be dealing with Fk, which is mu-Kn, and this little bugger is going to go to the right because by property he has to go opposite the direction of motion, and the direction of motion of B is towards the left. Therefore, and let's call this directly mu-K times N, because that's the force, Fk. Good. Thank you. All right. Next one, A. So we're normal force. So normal force, obviously, acting on A from B is going to be up. What label are we going to be able to give that normal force? As we use Newton's third law between system A and B. Remember, the third law is always between two systems, while the first and second law is always acting on a system. Yeah, excellent. Thank you, Tyson. It's going to be opposite to NAB. Technically, it's NBA, but by Newton's third law, we know the magnitude is the same, and we're going to flip the direction to represent the negative sign, which I forgot in my Newton's third law. Well, perfect. So this is NAB. Perfect. Good. What else? Is there any pushing, pulling? There is no pulling except from the string. So there's a tension from the string, which obviously goes towards the left. Same question as the normal force. Do we know this particular force? Or if not, do we at least know its correct label? Using, again, Newton's third law, because the string connects A and B. Or do we have to introduce a new unknown? Excellent. It's going to be the same T. Perfect. And we are sure of this because of Newton's third law and because of the property of the pulley. Since we're not given any mass for the pulley, we know the tension is the same along the string, whether it is at equilibrium or not. In this case, the pulley is rotating, and yet we're still going to be assumed that the tension is the same. So we're using two things here, Newton's third law and the property of the pulley, which again we're going to lose in chapter 10. Perfect. Now if B, so now the last one on the list is friction. Same, we're dealing with kinetic. But if B is going left and is connected through object A by that string around that pulley, then obviously A is going right. Therefore, the direction of the kinetic friction must be in which direction? Excellent. Thank you, Drew. There is the left. And this one is mu-Kn, but the N, the normal force that we're going to use is NAB. Okay? Are those complete? Are we all satisfied with those free body diagram, or is there something else? Yeah, there are two frictions. Exactly. B has some friction from A as well. The nice thing about Newton is you can always imagine that you're the system you're investigating. So imagine that you're B. Imagine your head is towards the left and your toes are towards the right and you're being dragged towards the left. You're obviously going to feel some friction on your belly. That's the friction between you and the floor. And you're going to feel some friction on your back from object A. What is going to be the direction of that friction between A and B? Is it also going to be towards the right or is it going to be towards the left? As object A slides towards the right on top of object B, if you imagine that you're B, what is going to be the direction of that friction? Excellent. Imagine that A doesn't move and look at the relative motion between A and B. If you hold A fixed as your reference, obviously B, with respect to A, still goes towards the left. Therefore, friction has to go towards the right. And this one is going to be mu K and AB. So be careful when you have more than one friction. The friction is always expressed in terms of the corresponding normal force. So the friction between A and B involves the normal force between A and B. But the friction between B and the floor must involve the normal force between B and the floor, which I've called NF. Therefore, I need to make sure I have the same label. Otherwise, I have an NF, I have an N, I have an NAB, way too many unknown. Okay, are we good so far? So we can write two equations from the top, two equations from the bottom. We have four equations. How many unknown do we have? We have F. That's what we're looking for. We have NF. We have NAB. And then from the bottom, we have NAB, but it's already counted. And we have T. Good. We have four unknown. We know we can write four equations. That's it. The rest is just math. We go back to chapter 2. Good. So let's pick a coordinate system. All our forces are up, left, and down, right. So let's pick X here, Y here. So our projection vector is going to be easy. When you're moving at constant velocity, you don't have to pick the positive X in the same direction of motion because the right-hand side is 0 anyway. It's only when you have an acceleration. So I don't have to pick my positive X towards the left for object B. Again, because the right-hand side is 0. Remember that you don't have to pick consistent coordinate system between two subsystems if you don't want to. It's usually strongly suggested if there is an acceleration, as we've seen in previous Newton's problem. But if it's at equilibrium, which includes constant velocity, it's up to you. Cool, that's it, done. So, two equations from the top. We're going to have, in the X direction, we're going to have 4 mu K NAB plus mu K NF plus T negative F is equal to 0. And in the Y, we only have 3, and F minus NAB minus WB is equal to 0. And from the bottom, even easier, T minus mu K NAB, that's equal to 0, and NAB minus WA is equal to 0. Done. 4 equations for unknown, bing, bam, boom. We're after F, so we want to solve for T for sure, which we can get from here, but that means we need NA, so we can solve it from here. So equation 4 will give us NA. We substitute NA in equation 3, then we get T, then we substitute T in equation 1. We also substitute the NA from equation 4 back into equation 1, right here. And then now the last one is to go after NF, the second term, which we can get from equation 2, after we substitute NA from equation 4, and then we can solve for F. So let's practice a little bit of algebra. F will be mu K NAB, and NAB is WA, plus mu K NF, and NF can be obtained from the second equation, which is WB, plus NAB, which is WA. And then T, which is from the third equation, mu K NAB, which from the fourth is nothing else but WA. And that's it. Oh, wow. So you can simplify quite a bit. UKWA, 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 so that's 3 of them. And then UKWB, only 1. So I can factor out the mu K. And that would be the magnitude of F. Gotta be positive, because it was given to us, so the direction was known. Okay? Questions on this? Drew, in the third, NW and WB are in parentheses. Did I goof somewhere? In the 3 and WA. When you say 3, you mean equation 3? 1, 2, 3, 4. WA and WAB in parentheses. Oh. You mean, bang, I forgot the W. Thank you. Is that what you meant, Drew? And then both are within the parentheses because I factor out mu k. I have one mu k WA, another mu k WA, another mu k WA, those are last 3. And I have one mu k WB. Perfect. Thank you. Yeah, WB. And then we just plug the numbers. So WA was 1.4, 3 times. WB was 4.2, 1 time. And we multiply the whole sum by which one? It's going to be the smallest one, so 0.3. Cool.